Fields. Well, not that kind of field. Today we're talking about fields in physics, and fields are things in physics that you can't see, except if you have some kind of superpower. You can only observe their existence if you test it with something that would feel a force in this field. And today we're going to talk about the three fields that you'll encounter in the IB program, which are the gravitational field, somewhere where a test mass feels a force, an electric field where a test charge feels a force, and a magnetic field where a test magnet feels a spinning force. Okay, so let's start with the gravitational field. A gravitational field is generated by a mass, and here I took the Earth as an example, which is a spherical mass, and therefore will generate this kind of pattern around it for the gravitational field. These lines are a pretty neat way to represent how a gravitational field is in a region of space, because it says two things about the field. It says how strong it is at different places using the distance between the lines. When the lines are close to each other, it means that we are dealing with a stronger field, and when they are far apart from each other, we're dealing with a weaker field. And that makes sense, right? Stronger field close to the surface of the Earth, weaker field as you go further away. Another nice thing it says, a useful thing it says, is that if I place a test mass here at a point in space, well, I can predict the direction of the net gravitational force, which is in the direction of the field line itself. Here, the net gravitational force will be in this direction. So here's the force that a test mass would feel. Now this little picture helps us define what gravitational field strength at a certain point in space is. So imagine I want to measure the gravitational field here. Well, the only way I can do this is actually to place a mass here, because this is the only thing that can feel a gravitational field. And when I place this test mass, I measure the force that it's feeling, and I divide it by the mass of this test mass itself. So this is how I obtain this formula, G equals F over m, which is the defining equation for gravitational fields. And in the case of a field generated by a sphere, we obtain the following interesting result. The strength of the gravitational field, G, is equal to this gravitational force, so therefore the universal constant G times the product of the two masses divided by the distance squared between the two masses, and all of that, okay, the force, divided by the test mass. And here we see an interesting thing, which is that these cancel out, the test mass cancels out, and we're left with the gravitational field being equal to Gm over r squared. And we can use this formula to verify that the gravitational field at the surface of the Earth, the strength of that field, is indeed 9.81 newtons per kilogram by plugging in the data. Okay, the gravitational constant, 6.67 times 10 to the minus 11, times the mass of the Earth, divided by the square of the radius of the Earth, okay, about 6,370 kilometers. And if you plug this into your calculator, you indeed verify that you obtain 9.81, and we have newtons per kilogram, because if you look at the defining equation for gravitational field, indeed we have a quantity in newtons per kilogram. Near the surface of the Earth, we have a uniform gravitational field. Uniform because it has a similar direction and strength everywhere. Okay, it's towards the ground, and the strength of the gravitational field is 9.81 newtons per kilogram. And now what's interesting is that this 9.81 value also expresses the acceleration of a free-falling body. If I have an apple that's freely falling towards the ground, it has an acceleration, a, which is equal to the net force acting on this apple divided by the mass of the apple. And since the net force on the apple is its weight, okay, and we learned that the weight on an apple or any object is equal to m times the gravitational field, well, here we have mg divided by m. In the end, we have an acceleration that is equal to g. So this 9.81 Newton per kilogram is in fact also 9.81 meters per second squared, the acceleration of any free-falling body near the surface of the Earth when you neglect air resistance. Now imagine that I'm in a space shuttle here, and I'm making the problem easy here by making a right angle between the direction shuttle to Earth and shuttle to Moon. And I'm intrigued by something. I'm in the space shuttle and I'd like to measure the acceleration on that shuttle due to the gravitational field. But the gravitational field here is generated by a combination of two fields. The one caused by Earth, okay, which is in this direction. So here I have a first field of strength Gm over r squared, where r is the distance RE, let's call it, and ME, and RE is the distance between the shuttle and the center of the Earth. And then I have another field, which is caused by the Moon, of strength. So this is, let's call it Gm, and the other one Ge. Okay, and this Gm is equal to another Gm over r squared, but this time with the mass of the Moon and the distance compared to the Moon. So now the trick question is, what is the direction and the magnitude of the net gravitational field by this space shuttle? Well, this is where you have to practice vector sum. In fact, the resultant gravitational field at this point in space is the sum between the green vector and the blue vector. So I have to put them end to end. Okay, let's start with the green vector, to which I add the blue vector. So the resultant vector is this, going from beginning to the end of my sum. And this is the net field. And its strength, is it Ge plus Gm? Well, no, look, we have a right triangle here, and the length of this arrow is, according to Pythagoras' theorem, the square root of the sum of the squares of Ge and Gm. Okay, so that's a bit tricky. You have to make sure that you apply vector sum when you add fields together, because we're adding vectors together. We're not adding scalars. Now, electric fields. The logic is rather similar to gravitational fields, except that we're looking at test charges feeling a force at a region in space and not test masses. And a test charge will, of course, feel a force in a region in space if there is an electric field generated by a charge. So if I have a positive charge, it will generate that kind of field around it, and a negative charge, that kind of field around it. So here we have field lines that are pointing radially outward. And why did we choose this convention? It's because, according to the convention, if I have a positive test charge, which is what I conventionally test an electric field with, so I have a positive test charge Q, well, it will be accelerated radially outward because positive charges repel each other. And if I put the same positive test charge in a field generated by a negatively charged sphere, it will be attracted towards the center of the sphere and therefore radially inward. And the letter for the variable we usually use for electric fields is a capital E. So in both these cases we have a vector E to represent the field. And what is the electric field strength? Well, similarly to the case of gravitational fields, it's the force felt per unit charge by a small positive test charge. Okay, it's small not to distort the field and positive to respect the convention. So the force felt per unit charge by a small positive test charge at a point in space. So the defining equation of the electric field is E is equal to the force F that it feels divided by Q, the amount of charge that I use to test the field. And what if I want to generate a uniform electric field? Well, I can just charge two plates and put them in front of each other, and between the two plates I will have a uniform electric field with a bit of edge effect here on the edges, a bit of curvy electric field on the edges. And this is basically what a battery looks like. Okay, there's an electric field that is going from plus to minus. And if I connect a wire between the positive side and the negative side, I create a circuit with an electric field that goes from positive to negative. And this is the direction of what we call the conventional current that we usually write I. And the electrons, as you know, are accelerated in the opposite direction from negative to positive, because remember that the electric field accelerates positive test charges in this direction. So if I have a negative test charge, it will be accelerated in the opposite direction of the electric field, and therefore the opposite direction of the conventional current. And these two pictures now show the electric field pattern generated by two charges of equal amount, but here they're opposite signs and here they're similar signs. So this rather makes intuitive sense. Okay, I'm not going to dig into explaining this, just notice that here all the field lines are pointing towards the negatively charged sphere, and here all the field lines are pointing outwards. And here they're always pointing outwards because we're dealing with positive charges. And another interesting thing to look at is, well, let's verify that it makes sense. If I place a positive test charge here, it will be affected by this. Okay, so I will have a field in this direction, and by that, so I will have a field in this direction. And indeed, if I make the sum of the two vectors, I obtain an arrow that looks like this, a net arrow that looks like this. So it looks like, yes, indeed, the particle, positively charged particle here would be accelerated in this direction when standing at this point. When you draw electric field patterns, make sure that you respect a set of simple rules here. First of all, you should never go inside the object that generates the electric field. Okay, that's also, of course, valid for gravitational fields. And the field lines that start from the surface, okay, you should start from the surface, well, they have to be perpendicular to the tangents to that surface. Okay, so here I'm drawing all perpendicular lines emanating from the surface. And why is that? Why does it have to be perpendicular? Well, if it wasn't, then it would mean that the next line that I would draw would cross this line, and that's not allowed. You can't cross field lines. Okay, now why can't you cross field lines? Why doesn't that make sense? Well, let me draw this absurd situation where field lines are crossing. Well, it would mean that at that point, at that specific point, a particle would be accelerated in two directions at the same time, and that's not possible. Imagine I drop a positive test charge here at rest and I let it go. Well, it can't go in this direction and that direction at the same time. It has to go in one direction. So this is why this kind of drawing doesn't make sense, and field lines never cross. And last, for all the field lines that are exiting your surface, make sure that you have a similar distance between your field lines, okay? Because if I add another one, suddenly I'm showing something weird, which is that the field is stronger here than the rest of the places around the circle, okay? Remember that the distance between two field lines expresses how strong the field line is. And since it's as strong all around the sphere here, this doesn't make sense, okay? So don't do that either. Finally, moving on to magnetic fields, which are regions in space which affect test magnets. And in fact, they don't accelerate them, they make them feel a spinning force. They make them spin. So a magnetic field can, for example, be generated by a bar magnet. Okay, it's for more explanation on the fundamental nature of magnetic fields, you should watch a Veritasium/Minute Physics video, which is very nicely done on this. So here I'm just going to explain some basic things. Here's the magnetic field pattern that looks like around a bar magnet, radially outwards from the north pole of the magnet and radially inwards towards the south magnetic pole. And how do I test the magnetic field at a point in space? For example, here, well, I take a compass, which is in fact just a simple test magnet, which has a north magnetic pole and a south magnetic pole as well. And what this compass will tend to do is to align itself such that the north is attracted by south, and south is attracted away from south. It's repelled by south. So it will align itself in this direction. And this is what the direction of the magnetic field lines express. It's the alignment of a test magnet in the direction of this line. So here our compass will be will turn towards this south magnetic pole. And this is something that's quite confusing to students, but when you look at planet Earth, which behaves in fact like a huge bar magnet, see, you can look at the magnetic field patterns and you see that they're quite similar to the bar magnet. Well, the geographic North Pole, so where there are the polar bears and everything, this is actually the south magnetic pole. This is the south magnetic pole, because if I take a compass, well, the north pole of the compass will be attracted towards the south magnetic pole. It makes sense, right? So the north pole of the compass is pointing towards the geographic North Pole, meaning a south magnetic pole. Magnetic fields are generated by bar magnets and moving charges as well. If I have some electrons moving in this direction in this wire, well, it means that I have a current in this upper direction. So currents in general generate magnetic fields, as you can see with these circles that represent the magnetic field pattern generated around this current carrying wire. So you can use another right-hand rule that you can call the field right-hand rule, or the curly finger right-hand rule, where you put your thumb in the same direction as the current and you grab the wire in your hand, and the fingers, the curling of the fingers show the direction of the magnetic field that's generated by this current. And of course, these concentric circles become larger and larger because the field becomes weaker and weaker as you go further away from the current carrying wire. Now that we have this trick to figure out the direction of the magnetic field, what about the strength of the magnetic field? How do I determine the strength of a field? Well, let's work with a field that's a bit simpler to study than this curly field. I'll use a uniform field here, and I'll tell you later how you can generate a uniform magnetic field. So I have a uniform magnetic field pointing out of the page. Okay, this is a vector pointing out of the page. And to test that magnetic field, well, I have to have a moving charge. Only moving charges feel a magnetic field. So here I have a small positive test charge moving downward. So I have a current downward. And to figure out the direction of the magnetic force, I will use the force right-hand rule this time, not the field right-hand rule, not to confuse the two. So I have my thumb pointing downwards, my fingers pointing out of the page because the magnetic field is out of the page. And when I do this, well, you realize that your palm is directed towards the left. So this is the direction of the magnetic force. And the relationship between this magnetic force and the other variables is F is equal to QVB times the sine of the angle between V and B, but here V and B are perpendicular, downward versus out of the page, that's a perpendicular. So I'm left with the magnetic force equals to QVB. Therefore, B is equal to the force, okay, the strength of the field is equal to the force divided by the product of Q and V. And this takes me to the following definition for magnetic field strength. It's the force felt by a small positive test charge moving in a direction perpendicular to the field divided by the charge and its velocity. It's quite a complicated definition for a variable, but if you have this picture in mind and this relationship between these variables, B equals F over QV, well, it's actually rather easy to formulate. We have a few more questions to tackle before we become pros with magnetic fields, and then that will be it. So first, how can we generate a uniform magnetic field? Well, we can use what we call a solenoid, and have a current going through it. So here I have a current generator, it goes through a solenoid, and how do I figure out the direction of the uniform magnetic field created inside it? Well, how do I know if it's left or right? Well, I curl my finger. I use the field right-hand rule, and I test it here. And if I grab this part of the solenoid here, my thumb is pointing towards the direction of the current, upward here, and my fingers are going inside the solenoid. Okay, so this is how I figure out that it's going towards the left. So now that I have a uniform magnetic field, I can play with it to know how current carrying wires and moving charged particles move inside a uniform magnetic field. So let's take this first case. I have a magnetic field pointing into the page, a current towards the right. So thumb towards the right, fingers into the page. I obtain a force pointing up. So this is the magnetic force. And it tends therefore to accelerate my whole wire upward. And this force is equal to BIL, the magnetic field strength times the intensity of the current times the length of the wire. So if I want to find the acceleration on the wire, how much it's accelerating, I have to divide the force by the mass of the wire. So B times I times L divided by M. Let's say that M is the mass of my wire. So now what's going on with charged particle moving in a uniform magnetic field? We've seen this before, but we haven't taken it all the way. What's the trajectory that it's going to follow? Well, here I have a current towards the left, so thumb towards the left, magnetic field into the page, so fingers into the page. Therefore, I have a magnetic force pointing down. Okay, and so I have an acceleration pointing down and a velocity pointing left. I have a perpendicular relationship between these two vectors, and when I obtain velocity perpendicular to acceleration, that means that my acceleration is trying to change this velocity vector by deflecting it. So in fact, a bit later on, if I observe again where I am, well, I'll have deflected towards here, and the velocity will be pointing in this direction now. And the force, well, it will still be perpendicular to the velocity this way if you reapply the right-hand rule, and we'll have an acceleration again that's pointing towards what seems to be the center of a circle, which is in fact the trajectory of my charged particle. So a charged particle moves in circles in a magnetic field. And it's uniform circular motion, meaning that the speed stays always the same because the acceleration is never in the direction of the velocity, it's always perpendicular. And what is the force equal to? Here we saw that in this case it's equal to QVB. We saw that several times, QV times B. And therefore the acceleration is equal to what? The acceleration is equal to QVB divided by M, the mass of the particle, QVB divided by M. And something interesting is happening here is that when we have uniform circular motion, the acceleration is actually equal to V squared divided by R, where R is the radius of this circle. So we have V squared over R, which is equal to QVB divided by M divided by M. And by rearranging this equation, well, first we realize that we can divide by V on both sides, so this square disappears and this V disappears. And now we can express R in terms of the other variables. And if I multiply by R on both sides and take everything to the other side here, I'll let you do the math, but you obtain R is equal to mV over QB. And I find this result rather interesting because it means that if I know the mass of my particle, how fast it's moving, what its charge is, and how strong the magnetic field is, well, I can predict the radius of the circle trajectory that it's going to have. And the more massive and fast my particle is, the larger the circle is going to be, and the stronger the field is or the amount of charge, then the tighter my trajectory will be around that center. And that's it with fields.